Section 21.6, the activation of octahedral complexes. In this section, we'll talk about ligand substitution reactions of octahedral complexes. And this type of reactions usually go through the interchange mechanism. That means in the intermediate structure, the transition metal center forms a partial bond with the entering ligand. Meanwhile, the leaving ligand and the transition metal center still has a partial bond. It's partially broken. Now let's look at subsection A, leaving group effects. In ID reactions, here ID means interchange mechanism, dissociatively activated. In this kind of reactions, the leaving group has a large effect on the reaction rate constants. So experimentally, if you see this reaction rate constant depends significantly on the types of leaving ligands, well, then this is dissociatively activated. The dissociation step is the rate limiting step. How fast or slow this dissociation is determines the overall reaction rate. On the other hand, if you do experimental analysis and you find the reaction rate constant remains approximately unchanged, no matter what leaving group you're using, that means, well, this dissociative step is not the rate limiting step. And that suggests this mechanism is associatively activated. The first association step is the rate limiting step. So this is a simple way for us to determine whether an interchange mechanism is associatively or dissociatively activated. Now in this I sub D reactions, it's found that we have this equation, ln k is equal to ln uppercase K plus a constant. So this logarithm of the rate constant is equal to the logarithm of the equilibrium constant plus a constant. For example, in here, in this graph, we're talking about this reaction. We're using water to replace this X ligand. Water is the entering ligand, X is the leaving ligand, and this X is 6 different ligands, and you can see this 6 different ligands give you a different reaction rate constant. That means this mechanism is definitely dissociatively activated. The leaving ligand matters. All right, and also you see this trend here, the logarithm of this rate constant and the logarithm of the equilibrium constant, they just differ by a factor. Just differ by a constant. I think the constant, we can determine this here. The constant is roughly -6. So when the logarithm of k is 0, the logarithm of this rate constant is -6. So in this case, this constant is -6. All right? And this is almost perfectly linear. Okay? And because we have this Irene equation for the reaction rate constant, and we have this equation for the equilibrium constant. And then we take the logarithm of both sides and we do some more analysis. We find this Gibbs energy of activation is approximately equal to the Gibbs energy of reaction plus a constant B. Okay, this is a different constant. Okay, so in this case, if you look at this equation, over here, this is the Gibbs energy of the transition state minus the Gibbs energy of the reactants. This is the Gibbs energy of the products minus the Gibbs energy of the reactants. All right? Now let's look at cobalt 3 complexes. So over here we're looking at cobalt 3. You can see over here oxidation number is 3. Over here it's also 3 because this X bears 1 negative charge, right? And now if you look at all these ligands, nitrate, dido, bromido, chlorido, etc. If you look at all those ligands. So this nitratol ligand leaves the fastest, fluorine minus the slowest. And then if you just look at this iodido, bromido, chlorido, and fluorido, well, they are in the same column as you see the trend. And why is that? Well, it's because cobalt 3+ is a hard Lewis acid. It binds strongly with hard Lewis base. So iodido, bromido, chlorido, fluorido, they are all Lewis base. Lewis base means they can give away electrons. Lewis acids can accept electrons. This cobalt 3 transition metal center can accept electrons from the ligands. And those iodido, bromido, chlorido, fluorido ligands can give away lone pair electrons to form a single bond. All right? So there's a so-called hard-soft acid-base theory about the strengths of the bonds between Lewis acids and Lewis bases. So hard acid and hard bases bind strongly. Soft acids and soft bases bind strongly. So in this case, cobalt 3+ is a hard acid. I'm going to explain what's hard, what's soft later. So cobalt is hard. Okay? And fluorine minus is hard. That's why the bond between cobalt and fluorine minus is stronger than the bond between cobalt and chlorine, and it's stronger than between cobalt and bromine, stronger than cobalt and iodine. Okay? And now I'm going to talk about hard and soft. So if we're talking about a hard acid, well, that usually means it has a very high oxidation number, in this case 3+. And also hard acid usually have a small size. So this is a 3D transition metal with 3+ charges. The size is really small. And also with small polarizability. When you have 3+ charges, the electrons are strongly attracted to the nucleus. It's very hard to change the electron distribution surrounding this cobalt 3+. That's why cobalt 3+ is a hard acid. Now let's look at the bases. Okay, we have 1, 2, 3, 4 Lewis bases in the same halide column. Fluorine is the smallest. All right, iodine is the largest. Fluorine has the smallest polarizability, so it's a hard base. Iodine has a very large radius. It's easier to change the distribution of the valence electrons in iodine minus. So iodine minus is really soft. And this is a hard base. It binds with this cobalt 3+ hard acid really strongly. So that's why it's very difficult for fluorine minus to leave this cobalt 3+. Okay, that's why. Also, there are also solvent effect. I think this nitratol ligand can be really well solvated by surrounding molecules, so it's easier for this to leave. And also, this is, of course, pretty soft with a very large size. Okay, it's easier to change the distribution of electrons in here. Okay, that's the hard-soft acid-base theory. But I would like you to do Control-click of this to go to this LibraryText.org website to learn a bit more about hard-soft acid-base theory. In summary, hard acids and bases, they usually have smaller sizes. They have higher oxidation states or higher oxidation numbers. They have smaller polarizability. Soft acids and bases, they have larger size. They have lower oxidation state or lower oxidation numbers. They have larger polarizability. It's easier to change the distribution of the valence electrons of those soft acids and soft bases. So you can learn more about this, and you can see more examples in this webpage. Subsection B, the effects of spectator ligands. So spectator ligands are those ligands bonded to the transition metal. They are not leaving the transition metal. Spectator ligands that are strong sigma donors can stabilize the transition state. Well, if they are strong pi acceptors, they can also stabilize the transition state. So that can increase the reaction rate. All right, so let me give you one example. Over here, we are using this aqua ligand to replace this X minus ligand. This X minus is the leaving ligand. This aqua ligand is the entering ligand. So this reaction is faster when these 5 ligands are amine ligands than aqua ligands. So if you have 5 amine ligands instead of 5 aqua ligands here, the reaction is faster because the 5 amine ligands are better sigma donors and they can stabilize the transition state better than 5 aqua ligands. Subsection C, steric effects. If you have a really bulky ligands, the steric crowding favors dissociative activation. This is obvious. Okay. Dissociative activation means, well, you have fewer ligands in that step, and when it's crowded surrounding the transition metal center, it's favorable to remove one ligand from the transition metal center. All right? And again, that means, well, this dissociative reaction reduces the steric strain caused by the bulky ligands. Subsection D, activation energetics. So if we look at the energy barrier, that's the difference between the energy of the transition state and the energy of the reactants. In the transition state structure, you can also have ligand field stabilization energy. All right? But then we can define this ligand field activation energy. So that's the change of the ligand field stabilization energy when the reactants become the transition state. Okay, there's a difference here. Okay, usually the LFSE in the reactants is greater than the LFSE in the transition state. All right, so when you are looking at the energy diagram, when you go from the reactants to the transition state, there's going to be a loss of LFSE. Okay, when you have a loss of LFSE, that will make the energy barrier larger. All right, you need additional energy to compensate this loss of LFSE. Okay, the transition state is even less stable or higher energy than the reactants. So that in that case, that will make this energy barrier larger, the reaction rate constant smaller, and that means this reactant complex is more non-labile. Non-labile, that means it's more stable, it's more difficult to replace one of the ligands in the reactant complex. Subsection E, associative activation. So this means the first associative step is the rate limiting step. So in this case, the entering ligand matters. The reaction rate constant depends on the entering ligand. All right? So the reaction rate constant changes when you use different types of entering ligands. That's an indicator of the associatively activated mechanism. And also, you can determine the entropy of activation and volume of activation. If both are negative, and then you can be sure that the transition state structure is more compact than the reactants in the rate limiting step, right? And then if you say, well, the transition state structure is more compact than the reactant, that's got to be association, right? And then this rate limiting step is an associative step. and this mechanism is associatively activated. And in this I sub A reactions, this subscript A stands for associatively activated. The entering group matters. It has a very large effect on the reaction rate constant. Okay, and also experimentally, if you try different types of entering ligands, and you see quite different reaction rate constants, that means, well, this mechanism is associatively activated.